Okay, well, today, if everything goes well, we'll have Dallas joining us to talk about odd tin-bearing showers of cosmic dust. Are they from Comet Halley? So I know a lot of you remember Halley's comet from '86. Not too many from 1910. But in 1910, it was a lot closer to the Earth and a lot more visible than it was in '86. That was one of the reasons Bill Halley was able to come up with a name for his group. But Halley's comet appears on the Earth, or from it appears at the Earth every 75 or 76 years. So it will return in 2061. And it was named after Edmund Halley, an English astronomer in the 17th century. I'll have more about him later. The urban legend is that Halley asked his friend Isaac Newton if it would return. So Newton sat down and figured out mathematics, calculus in particular, provided an answer of yes and when. Wasn't quite like that. I got some more information later. But associated with Halley's comet is a meteor shower called the Eta Aquarids. They move about 152,000 miles per hour, and there's about 60 per hour. They're in the Aquarius constellation, and they've been known since the 8th century, observed by the Chinese. Mm-hmm. Although the connection to Halley's comet wasn't made until 1900. And as many of you know, meteor showers are named after the constellation that they're against. And in this case, it's the Aquarius constellation. Mm-hmm. They were first recorded in the 8th century, but in 1868, people suspected that Comet Halley and the Eta Aquarids were related. That was confirmed in 1900 by an astronomer named William Denning. Mark Twain, or Sam Clemens, was born in 1835 and often made the statement, "I was born with Halley's comet and I'll go out with Halley's comet."
And he did?
Yep. A few months after Halley's comet appeared in 1910, he passed away. Mm. So a comet is a small, icy solar system body. When passing close to the sun, it warms up and begins to release gases, which produces a visible tail or coma. The exact number of comets varies between 4584 in Wikipedia and 3743 in NASA. Mm. The name means hair and refers to the long hair-like features. Comets have highly eccentric elliptical orbits, which means they have a wide range of orbital periods, ranging from several years to several million years. Short period comets, we think, originate in the Kuiper belt, and long period comets come from the Oort cloud. Mm. Asteroids and comets are both small bodies orbiting the sun. The asteroids have elliptical orbits shorter than those of comets. And there are millions of asteroids, many in the asteroid belt between Mars and Jupiter. They range in size from kilometers across to dust. They're made primarily of metals, rocks, and organic matter. Comets are made of ice, rocks, and hydrocarbons, and they form the temporary atmospheric tail. Although some of you remember a few months ago, the DART mission smashed into an asteroid, and images now show that it has a double tail. The nucleus of the comet is usually from 1 to 10 kilometers. So now I've got a bunch of slides on the brief history of comet observations. Comets were probably known before Aristotle, but there are no records. But by the time Aristotle started to write things down, it was pretty clear that people had known things for a while. Comets were considered bad omens, predicting the death of leaders of catastrophes. Let me, for some reason, repeat that. This looks like a slide I'll have to edit a little bit later. In China, they have things called oracle bones. And some of the oracle bones known that they would show that comets were known about for thousands of years. The Chinese diviners who advised the emperors. The diviners studying comets advised emperors. And in 712 CE, an emperor named Ruizong of Tang abdicated because of a comet. And in 35 CE, the breakup of a comet that was observed led to the end of a rule by a warlord named Gansu Shu. In Norse mythology, comets were thought to be flakes of a dead giant skull, giant having been killed by Odin and the other gods. One of the most famous comets of the past is commemorated in the Bayeux Tapestry, which was woven a few decades after the Battle of Hastings in 1066. The comet was observed and it was connected with the death of King Harold, the last Saxon ruler. It's thought that that was Halley's Comet. The Bayeux Tapestry is 70 meters long, 50 centimeters wide. Aristotle rejected the idea.
Okay, yes. So basically, these odd tin-bearing showers of cosmic dust. Our original work, which was published in 2015, suggested that they came from Comet Halley, but we have a lot more recent data. And so we're suggesting, and so now we think that there may be some other comets involved, although maybe not very many. So that's sort of the summary. And also, I had to figure out, like a lot of cosmic dust contains iron and nickel, which is weird because comets are supposed to be this stuff. They're mostly like, they call them rocky snowballs. They're mostly made out of, all these volatiles, and they're supposed to be stuff that had a low condensation temperature. So the iron and nickel don't have low condensation temperatures. They have very high melting points. So I've been kind of wrestling with that issue. So first of all, extraterrestrial dust or cosmic dust. What is it and where does it come from? So here's two figures. One is, this is the thing on the left is porous cosmic dust. And the stuff in the back, that's just like they use this stuff called a aerogel to collect it. So they put it up in space and then you get these bits of dust that land. And this is the typical vision of what cosmic dust looks like. However, as I'll show you, the stuff that makes it to the Earth without melting really looks pretty different. It looks kind of flaky, actually. And cosmic dust important because here's the particle sizes. So you're going, it's an exponential scale. So you're going from 10 to the minus 4 to 10 to the second. So the large impactors provide about half of the mass influx. And then the cosmic dust provides the other half of the mass influx. And notice that the visual meteors are actually larger than the typical dust. So this picture of the dust has a scale bar of 1 micron. So this whole thing is like 10 micrometers across. It's really small. And most of it, when it comes down, you can't actually, see it. It's just sort of coming down silently. The bigger pieces which produce meteor showers, which you can see at night, but that they're actually burning up. They're not making it to the ground. Okay, so possible sources of cosmic dust. People don't normally think of cosmic dust. I mean, people think of astronomical locations, but there's actually a bunch of kinds, and we're not totally sure if of the stuff that we see on the Earth, where does it all come from? So there's interstellar dust, which is between stars and individual galaxies, and there's intergalactic dust. And the importance of these sources of dust is that it's really cold out there. And because we're finding this dust with tin in it, tin has a very low melting point. So wherever it's coming from, it probably comes from someplace that's really cold all the time. And then the other origins of cosmic dust, so it could be either interplanetary dust found in the zodiacal cloud. So this is a picture of the zodiacal cloud. So here's the Milky Way. That's our galaxy, and here's the zodiacal cloud. So so the idea is, and during different times in Earth history, the zodiacal cloud has been brighter or darker, depends on how much dust it's got in it. And basically the reason why it's shining is because it's reflecting light. They're dust particles, and they're getting light from the sun. And then you also have circumplanetary dust. So here's an example, the planetary rings of Saturn. So, and also the zodiacal dust can make the sky brighter on moonless nights. So if you have a lot of zodiacal dust, it wouldn't really be that dark out at night. So the more traditional view of cosmic dust, people don't normally think about things like asteroidal, about intergalactic dust. They just divide it into dust from asteroids and dust from comets. And so asteroids are rocky bodies, and they come from things in the inner solar system. So stuff from the asteroid belt into Mercury. If a piece of it breaks off, you get an asteroid. Comets are dirty snowballs, so they have very high contents of low melting point things. This picture of a comet, one of these is part of it's an ion trail. So this is charged particles, but this part is stuff that's degassing off the comet. So comets, you can't normally see them when they're far from the sun. They're just, they end up with, a black coating of dust, and they're not degassing. So the reason why you're seeing the comet as it gets close to the sun is it gets hot enough to start to degas. And then of course, the coating, the dark coating on the comet gets removed as it degas. And they used to think that most cosmic dust was from asteroids, but actually the cosmic dust that reaches the Earth, about 95.4%, has a high carbon content. And that means it comes from comets or other extraterrestrial bodies that accreted far from a star. We're not, so far we're saying we don't know what these other extraterrestrial bodies necessarily are. There might be things that aren't strictly comets. So the thing is, so there's a lot of things we don't really understand about cosmic dust, because most unmelted cosmic dust, and I'll show you some images of this, it's platy with a high iron or nickel content, but it also has a high carbon content. And this is surprising because it means that comets must somehow pick up iron and nickel, and they both have high melting points. But so comets can contain high melting point material, but where do they get it from? And the interesting thing is that no reports of cometary compositions have ever mentioned nickel or other high melting point refractory elements like iridium. But both of these elements are considered markers for extraterrestrial material. And it may be that if you have a large comet you have enough nickel and iridium in the rocky bits. But there's definitely evidence for iridium associated with bodies that from their chrome isotopes are considered to be cometary. E.g. the KT impactor was probably cometary, and obviously it did contain some nickel and some iridium. But when people look at comets, distally and try to get their composition, nobody ever says, oh, we see nickel, oh, we see iridium. And part of it's, well, for iridium, it's very difficult to detect. Nickel, it's a little surprising. And then a very small proportion of cosmic dust contains tin. And the importance of tin is that it's a low melting point element. And the tin occurs sometimes, we've seen it actually quite often with aggregates of iron, nickel, chrome, and manganese. And Paul Laviolette did a lot of work on these tin-rich grains. And he looked at every single one of a large catalog of cosmic dust grains. And there were 983 grains in this catalog, and there was one grain containing tin. So basically, cosmic dust containing tin is very rare, 1 in 1,000, at least what we see on the Earth. And if you look at the literature, there's less than 10 papers discussing this tin-bearing carbon-rich cosmic dust, and thousands of paper on just the carbon-rich cosmic dust. So meteor showers have very high estimated velocities. So I'll be talking a lot about meteor showers. And so here's the velocities. So the Perseids, which are in August, they come from comet Swift-Tuttle, 60 kilometers a second. That's fast. The Leonids in November, 71 kilometers a second. And they come from comet Tempel-Tuttle. The Geminids have a velocity of 35 kilometers a second. They're almost the slowest on this list. Now their parent body is Phaeton, and some of the meteor showers are probably, they sort of look asteroidal in some of their characteristics, but they think they're probably a degassed comet. So that's consistent with the centers of a lot of comets having some more rocky material. And the Eta Aquarids in May, they're from comet Halley, and they come in at really pretty fast. They're at the high end, 66 kilometers a second. The Taurids in June and November come in at 29 kilometers a second. They're from comet Encke. The Retids, May, June, July, 39 kilometers. They don't really know the source comet of that. So basically, comets have higher average velocities than asteroids. So dust from comets should, in theory, enter the Earth's atmosphere at a high velocity. But the problem with that is if it did, it would produce large quantities of microspherules. And actually, in the stuff that we looked at in the ice core that I'll talk about, we found a few microspherules, but we found more grains that just looked like cosmic dust. And so the question is, okay, well, what it says is that basically means is that not all of this stuff can be coming in at the average velocity of the parent body. Some of it must be coming in more slowly. And see how I got it backwards. So the cosmic dust we found is tin bearing, is either a porous aggregate or an inclusion in a carbon-rich platy grain. The latter grains are large, they're 38 to 125 micrometers in diameter. So they must have settled slowly through the Earth's atmosphere, because if they didn't settle slowly, then they would have melted. And there's no evidence that these things melted. So they didn't come in at a high velocity, and they settled slowly through the Earth's atmosphere. So why are we seeing so many metallic grains, flat grains in the larger size of cosmic dust? I think the answer is that the larger round grains, they burn up in the atmosphere, and they're not in the inventory of cosmic dust that actually lands on the Earth. And these include some carbonaceous nickel iron bearing grains and carbonaceous olivine rich grains. And the vaporization of these rounder grains produces meteoritic smoke. Because basically if it's round, it keeps its velocity. It comes in, it keeps coming in quickly because it doesn't have a lot of air resistance. So here's some of the ions. This is from iron coming in. So basically you're ablating cosmic dust or meteorites, and you get this charged iron. And then this is the whole cycle of and and so here's what some of the things they think the iron's coming from. It's coming from pyroxene in the cometary of meteoritic material, and phaolite, which is an iron-rich olivine. And then here they've got hematite and goethite, which I find surprising because I thought most of the meteoritic stuff was not oxidized. But there's some reasons to think that a little bit of it may be oxidized. See, these are more oxygen rich. I would have put in magnetite in this diagram. And why is this meteoritic smoke important? First of all, it turns out that the phosphorus from the smoke, actually the most important biolimiting element, the elements that limit the growth of organisms, particularly in the mid-ocean gyres, places like the North Pacific, it's phosphorus is one of the biolimiting elements. So it turns out that you might have gotten a little more photosynthesis from things like diatoms when you've had more meteoritic smoke, because they bring in phosphorus. And the other thing that's pretty interesting is that the ions, and the major ones are iron, magnesium, and nickel. They can combine with water, carbonate, and sulfate. So if you have a lot of meteoritic smoke, that will probably disturb the sulfate signal in ice cores. So you'll get a rain out of the sulfate at lower latitudes from equatorial, you have equatorial mid-latitude eruptions, and then the sulfate normally travels to the poles and gets deposited in ice cores. But the ions from meteoritic smoke may combine with the sulfate, and so they may the signal of volcanic eruptions and ice cores may be changed. So that's kind of important. Okay, so the solutions are, first of all, that cosmic dust may spiral in slowly because it has to pass through the Earth's magnetic field, but that's not shown by the data. And I'm going to show you a lot of stuff. This is from Brownlow et al. It's a 1964 paper, but I haven't seen anything else like it. What they did was they collected cosmic dust on this mesh that they set up like right on the beach. Sounds like it was fun to do. They were in Barbados and in Italy somewhere, and they set it up in a place where the wind was coming off the ocean. And then they collected all these grains, and most of what they collected was iron and nickel. And here's one of them. Here's a very flat nickel grain, and then the red blob is the stuff that's oxidized, which maybe it's hematite. And you can see this is cosmic dust, but look at the size. This thing is like 200 microns by 50 microns, and then it's like, you can see it's incredibly thin. It's maybe a micron or two thick. And basically they looked at these grains and they measured them, and they're very flat, and their typical thickness to width to length ratio is 1 to 2 to 10. So basically these grains, they're part of meteor showers, but they come in and they settle very slowly because they're so flat. And so why do we see so many small of these flat grains? Well, I think the rounder, larger grains burn up in the Earth's atmosphere, and so they're not in the inventory. And these grains can include some carbonaceous nickel iron grains, and those produce, of course, the meteoritic smoke, carbonaceous olivine rich grains, and they also vaporize to produce meteoritic smoke. And so again, I said flat grains settle much more slowly, and the flat grains have this thickness to width ratio to length ratio of 1 to 2 to 10. And there's something called Stokes' law that you can use to calculate the settling rate of flat grains, and it's just much slower than the settling of round grains. And Brownlow et al., they're the only ones that have actual data on how long the flat grains took to get to the ground. And they estimated they took 2 days and an average rate of 1/2 meter per second. And look at the difference. The average velocity of the meteor showers is 29,000 to 71,000 meters per second. So you're talking about a huge decrease in velocity. So the flat grains, I mean, they're apparently part of meteor showers. It's kind of surprising that they have such a low velocity, but that's what the data shows. So here's some other observations. There were only 2 papers in the literature where they found these tin-rich grains. Again, this is a picture of the tin-rich grain, and you can see that it looks kind of flaky, which is what we see over and over. And it's, again, they're catching it on what's called this aerogel. So this is the carbon-rich aerogel. And normally, if you can take image, this is image with a scanning electron microscope, and you can image in 2 modes. You can image in what's called secondary or backscatter mode. And if you image in backscatter mode, tin will be very bright. If you image in secondary mode, which this is undoubtedly a secondary mode picture, the tin will, it basically shows you the textures, and the tin will look dark. So this is a picture in secondary mode. And here's the spectra of the tin. So tin has multiple peaks. Notice that the second tin peak coincides with calcium. So I think a lot of tin was missed because people, they thought it was calcium. And then this thing has chrome, nickel, and iron, which we found with tin-rich grains as well. They're saying it's contamination. I'm not sure I believe this. And tin X's were also reported in material from Tunguska. And they think that the Tunguska impactor came from the Taurid meteor shower, because it was about the right time of year. However, there's another meteor shower at that time too. So here's the second paper before we published our stuff, where they found tin that, unfortunately, their SEM image just looks like this black thing. I think it got published. I think it's the journal thing. I'm going to have to write the guy. But here's the tin spectra. So you can see multiple peaks. This is obviously an older machine. And the reason why they were willing to believe that this tin was primary and not something that, was like atmospheric contamination was because the tin was part of a grain that they were pretty sure was chondritic. So it looked like a meteorite. Although it's tricky when you talk about chondritic, because there is a type of meteorite that's very carbon rich, and it's considered a meteorite, but actually it's also, that's an analog for comets. It's called a carbonaceous chondrite. So, and here are the element abundances normalized to one kind of chondrite, a C1 chondrite. And you can see that, so here's tin. So tin, so tin is high. Tin is definitely much higher than you'd expect. And also bismuth is high and bromine is high. So, and these are all, I don't know about bromine, but certainly tin and bismuth have a very high have a very low melting point. So they're the kinds of things that you'd expect to be concentrated in comets. So those 2 papers, the Wright-Meyer paper and the Kiuchi paper, are the only ones. And unfortunately, Wright-Meyer doesn't say what time of year this cosmic dust was collected. I'll write him and try to find that out. So then we found all these tin-rich grains in the GISP-2 ice core, and they're part of, see how the tin is actually the part that's really, really bright. The rest of this grain is kind of this fluffy, kind of organic matter rich thing. And notice the sizes again. These things are really small. So like 10 microns by 10 microns. And we found them because we were looking for nickel in the ice core. And instead we found tin. We found some nickel too, but we were surprised to find these things. We didn't expect that they would be there. And another thing about these things, notice here's the tin, here's the spectrum, a little bit of iron. This one also has a little bit of copper. And notice there's silicon in there too. And another reason why we know that this is not, other than the fact that of course it looks like a bunch of cosmic dust, and it was found in an ice core where we washed the outside of the ice core, so you can't have contamination from to get rid of any possible contamination from terrestrial air. But here's a silicon peak. Now on Earth, tin occurs in ores, and but the amount of silicon here, the ratio of silicon to tin, is not consistent with it being terrestrial. So in addition to it being in this kind of fluffy, high carbon grain, the ratio of silicon to tin does not fit any kind of known terrestrial ore of tin. So we're pretty sure that it's extraterrestrial. Oh, and the other thing is you can't see it here. I'll show you later in a table. But when we modeled this tin, it turns out that the model fits best if we include some xenon in the tin. We see this over and over. And the xenon is probably a product of the tin being in the solar wind. And here's some more of these tin grains. Whoops. So that they're the really bright things. This one is iron actually, but this one is tin. And look at what's interesting is that these are all backscatter mode. As you can see that the tin is like brighter than the iron. And here you can really see it. Here's the tin, here's the iron. Again, the silicon to tin ratio is absolutely not what you'd expect for something that was terrestrial in origin. And then here's, this one is not something. And then again, there's a little bit of iron, but so these two are the tin grains. And you can see that there are actually 4 peaks of tin. That's really the best way that you can identify it. Here you can see the 1, 2, 3, 4. Here there's a lot of tin, so you can identify the peak. This was actually something that we're not sure about. Okay, so here's the observations. Now here is the model. Now here's the model on the left. See these peaks, these 3 peaks, and the blue is the model. And then the red in both cases is the data. And notice, particularly for these 2 peaks, that the tin, there's more tin than there should be, or there's more of a peak than there should be for what the amount of tin that we see in the main peak, because we use that the program uses that to model what it should look like. So there's some excess energy here that isn't explained by just tin. So it turns out that if we add both iodine and xenon to the spectra, you can see here, look at how much better it models. And also what's interesting is there's some nickel, there's some chrome, and there's some iron, and also copper and zinc in with this. And zinc and copper have been found in some of the other extraterrestrial things. And we find the nickel, iron, chrome too in with the tin. And so what we think is happening here, and we can really see it best in this particular sample, because this sample had the most tin of any sample, is that there's iodine in the sample, and that the xenon is produced from iodine by bombardment of the iodine by high energy particles in space. So here's yet more evidence that this stuff is not terrestrial. And again, there's a silicon peak, but the silicon to tin ratio is absolutely wrong for terrestrial ore. Okay, and so here are our semi-quantitative analyses. So we go from 23% tin to 69% tin. And most of them, we included all but one have some kind of xenon. And then this one was 3% iodine and 3.5% xenon. That's obviously the one I showed you. Iodine wasn't required for the others, but xenon was. So, and that's typical that we very often see xenon being required to fit the data, but needing iodine to fit the data is less common. Not quite sure why. And notice that some of these things have, like this one particle also had 2% nickel, which is, that's not a terrestrial rock. It had about the same amount of iron, it had zinc, it had almost 1% chrome, and it had copper and zinc as well. So this is a very unusual tin grain, and it only has 1.8% silicon. So when we looked at this data, we wanted to know what was the source of the tin-rich grains. And so what this is it's our data. The ice core basically came in like pieces that were broken, and so in order to we basically we had to melt it. First we washed off the outside with super clean water to get rid of any contamination, and then we melted it, and we just melted it in the pieces that we had. And so they covered different time intervals, and so that means that some of them covered less than a year and some of them covered about a year. And so then what we did was we took just the pieces that had either nickel or tin rich material in them, and we added them all together, the number extraterrestrial materials. And then, so the idea is that the peak here is when you get the most extraterrestrial debris coming in versus day of the year. And this is the time of the Eta Aquarids, which come from Comet Halley. So this is the basis of our claim that this stuff probably came from Comet Halley. And also what's interesting is there was a peak in Chinese meteor shower observations prior to 918. That's, so this data is from the 6th century, and this observation covers about the first millennium, Common Era AD. So basically it fits that during this period of time, the Aquarids now are not a particularly large meteor shower, but during this time they were very active. So it kind of fits. So this is the basis for our saying that the most probable source of the extraterrestrial debris in the ice core was Comet Halley. Okay, so here's some orbits of Comet Halley. So basically the comet, this is, the units here are astronomical units, and an astronomical unit is just the distance of the Earth from the sun. So Halley, has about an 85-year period. So it goes out. This is the furthest from the sun, and this is when it's closest from the sun, and it just keeps going in and out. And you can see that it came in, it made it closest to the approach about 5:30, and our extraterrestrial debris starts at 5:33 and goes to about 5:39, 5:40. So it makes sense. It first comes in, it leaves some debris, And also, these are the positions of the nodes, which is the distance from the sun. And this is when it's in this range, that's when Halley could be a source of debris for a meteor shower. Because there are two requirements for a comet to produce debris that ends up in a meteor shower. One is that the comet has to get at least past the Earth, closer to the sun than the Earth. But its orbit also has to be crossing because the Earth orbits in a plane around the sun. And so the comet has to be shedding debris into the plane where the Earth, so the Earth will actually cross its debris stream. And so these are the conditions when the Earth will cross its debris stream. And there are other times in the past when Halley has come in and it could not have produced debris that would end up in a meteor shower immediately, at least on Earth. Okay, so here's our most recent observations. And this is Corvima 33-116, 12 to 13 centimeters depth. And so here's a picture of this grain we found, and it's dark mostly, it's mostly carbon, and it's flat. And this grain ended up in a thin section. So we were picking actually for volcanic glass. This is like a bit of volcanic glass. And what's interesting is these bright colored grains here, these are iron, nickel, chrome. And then this is like pure tin. And the reason why we found this grain and realized something unusual was going on was because this is the core from the equatorial Pacific. And normally there's lots and lots of terrestrial organic matter and terrestrial material. And so you'd expect the entire core to be high in barium because that's correlated with terrestrial material. But in fact, this depth range, it's very low. The barium is below the detection limit in the XRF. And so we estimate that the age of this layer is between 800 and 389 Common Era, but we don't actually have an age for below that depth, so that's a rough age. So the possible cometary source we've got is 96P Machholtz or Encke. But again, my collaborator has to do some more work on the orbits. But the point is that it's probably not Halley. It's probably something different. Okay, so here's the same grain. Now here you can see this is in backscatter mode. And this was just, we put it on, and this is of the same thin section. I've just kind of prettied it up a little bit. So it's backscatter mode. So here's the tin grain, and this is the spectra. So here you can see all 4 tin peaks. And then these bright grains are iron, nickel, chrome. And then the rest of it, all the dark stuff, I thought maybe there was some mineral in here, but it's not. It's just all carbon. And from the age, this is all pre-industrial. So it's the iron, nickel, chrome is definitely not stainless steel. So this is, and also when we actually play with this image, it turns out that xenon's present. So this has that same characteristic thing as that we found in the ice core, that you really need xenon in with a tin to explain the spectra. Okay, so, and other people have found tin-bearing cosmic dust. Lonnie Thompson, he found one tin-bearing particle at a depth of 700 meters. The age is about 7,400 before present. And the source could be Comet Halley, but we really don't have models for the other comets right now that go back that far in time. I've got a collaborator who's working on it. Okay, and then here's I've talked to some of you before about Hudson River cores having tin-coated forams. And at the time we were like, what? And we knew it was all from layers that were pre-industrial. So I'll show you stuff but now we have some data, at least from this core, we've actually found some bits of things that look like cosmic dust in the cores. So the two cores I'm going to talk about are CDO213, CDO223 that were taken in the Hudson. And they were both taken in areas where I think maybe they dredged, but there's almost no modern sediment in these cores. And all of the samples that I'll be discussing are way pre-industrial. They're old. And we have carbon-14 ages on them. So we have fairly decent estimate of the ages. So here's one of them. So here's what the 4M looks like visually. We notice them because normally the 4Ms are kind of a bright white, and these things, see how that kind of orangey tint? So this is the 4M in visible light. This is the 4M on the SEM and backscatter. And again, notice that it's the bright stuff is the metal coating. Underneath is the 4M. So this thing, we had never, until we saw this, it was like, this was really, really strange. And again, here's an analysis of the coating. Because it's on a 4M, which is calcium carbonate, you get a calcium peak, but you definitely have tin too. And you also have silicon. So this is definitely tin, and it's coating the 4M, which is really, really strange. So, but we now know that there's cosmic dust at the same stratigraphic level. So what we think happened is that the tin was derived originally from cosmic dust, and then all the Hudson River cores are reducing, so they have very high contents of organic matter, and under those conditions, tin has to be mobile. And I think what happens is the tin migrates, and it kind of migrates in the pore fluid and precipitates on top of the 4Ms, because the 4Ms are oxidizing. This happens a lot in just all kinds of situations where you get like where uranium migrates in reducing sediments, and then it precipitates out when it encounters something oxidizing. And I think the 4M is oxidizing. So basically the age of this is about 173 plus or minus 67 BC. So the source comments would be Aaron Rigaud or Swift Tuttle. So another few comet names, not the same as before. And then we found two levels with tin-coated 4Ms in core CDO213. And the age of this one is about 500 to 800 BC. And again, it has so here's the tin-coated 4M. And again, you can see all these lovely, so the bright stuff are the tin crystals. And then you can see there's still some calcium in here because, I mean, it is a 4M, which is composed of calcium carbonate. And then again, there's this modest silicon peak and a slight aluminum peak. It would probably, that might be from clay. It's pretty difficult to get all the clay off. So, but look at this. I mean, the 4M is almost completely covered with tin crystals, which is pretty cool. And then here's the spectrum. And then the last tin-coated 4M, the level, we actually found more than one from this level. So this is CDO213. So here's what the 4M looks like in visible light. It looks just kind of yellowish. And then here's the same 4M on an SEM picture, and you can start to see that it's covered with crystals. And this is what the crystals look like in a close-up. And then with this particular one, we were able to get a thin section made. And this is just some kind of inclusion in the 4M, but this stuff here, this is the tin. And what happened was, I think what it shows is that the tin was not intrinsically part of the 4M, that it's actually a coating. And the coating, when they made the thin section, started to peel off. So, and then here's the EDS spectrum of the tin. And also notice there's some iron. And I should have labeled it, but I think there's some silicon as well. So in this case, the possible source comets, it's are Halley and Swift-Tuttle, and it's about 800 BC to 900 BC. So so we have at least 3 different layers in the Hudson with tin-coated forams. There's probably more because we haven't sieved the entire core. And what we're doing now is we're trying to get more data on just the barium content and try to sieve the low barium layers, because those are the layers that would have higher contents of extraterrestrial material. But it was really surprising for a lot of reasons to find this. For one thing, these are high sedimentation rate cores in a river. And I mean, the river, you should be getting lots and lots of terrestrial stuff. So if you're getting enough extraterrestrial stuff to produce these tin-coated forams, that's a very unusual situation. But you seem to be doing it, and you seem to be doing it at different times. Okay, so here, now we're moving from the Hudson to the observations of cosmic dust by Brownlow, because I just wanted to show you pictures of these things. So this is 30% nickel, 70% iron, and notice it's a flake. And it's big too. Here's 100 micron scale bar. So this thing is like 300, 400 microns long, and it's maybe 20 microns thick, and then maybe 100 microns wide. And so it's a flake. And so if it's got 30% nickel, 70% iron, it kind of has to be extraterrestrial. And then here's a pure nickel. Again, that has to be extraterrestrial. And these were collected in June. So their source, it could be either the Taurids or also I think the Perseids as a source. And again, this thing is big. It's like, 100, 250, 200 micrometers long, and maybe 80 micrometers wide. And it's a flake. Now here's the more typical carbonaceous thing. And here's the red stain, which they think might be oxidized metal, like hematite. And then the light stuff in this image, they must have taken it in secondary mode, is the carbonaceous material. So this is the stuff, the stuff that people typically think of cosmic dust, this kind of round, fluffy stuff. And then this is these flakes, which are pretty different. So here are their observations of cosmic dust. And this is how they got their settling rate. And I'm showing this figure because I tried to label it a lot, because I did not find this figure very intuitive. So what they're doing is these are the particle sizes, this axis, and then this is when the sample was taken. And then these lines are their estimates of the slope. And because they're doing 2 different sets of data, and they plotted, see this way, larger sizes are up, and this one, larger sizes are down. And so that's why the slopes look different. And the point is that you can see, particularly on this one, you can see that it looks like there are groups where the larger ones are up here, and then the smaller ones are down here. Let's see, that doesn't make sense. But anyways, this is how they get a settling rate of 0.5 meters per second. And you can actually see that they're kind of groups of particles. So these are nickel and iron, and these are pure nickel. The pure nickel flakes aren't as common, obviously. And they did this work in the summertime, so June through September. So that's why the data doesn't cover a full calendar year, because I guess they had academic jobs and they had to be back to teach. So they couldn't be in the field longer than that. And then here's another set of observations of cosmic dust. Here you got that slope. But it's not so obvious. But you definitely can see groups of these flakes that settled. Oh, okay. Oh, okay, here it makes more sense because it's actually showing sizes, and the sizes are getting smaller as you go up. So this must be, I think this must be an exponential scale. So let's go back to that because this makes more sense. Okay, so these must be like 10 to the minus 8 or something. So these are the smaller sizes and they settle more slowly. These are the larger sizes and they settle out more quickly. And so that's how they get the settling rate. And then so you have pure nickel flakes, you have nickel iron flakes, and you have, again, pure nickel flakes. I think this must be pure iron. Sorry, I must have mislabeled this. This has to be pure iron flakes because it doesn't make sense otherwise. So, and what you're getting is the smaller flakes take longer to settle. The larger flakes take a shorter time. And so then they took their observations of cosmic dust and they did cumulative mass. And so the iron ones, which are more abundant, are the X's. And then the ones with nickel are these guys here. And so basically they're showing that the argument here is that these are probably part of the same group. They're all from the same source. So these are the gamma Perseids and maybe the Iridids, and these are from the beta Taurids, common Enki, although actually they could also be from a part of the Perseids. And here's another location. And again, the thing is, what you're seeing is a pretty continuous size distribution until you basically run out of particles. Like the largest particle has a mass of about 7 micrograms. Over here, this is iron, and iron with some nickel, and it's about 7 micrograms. They were actually using a balance to weigh these things. And so basically this is arguing that, if you have natural size distributions, you have a pretty continuous distribution across sizes, and that's what you're seeing. So you have fewer large grains and more small grains. So where was nickel iron chrome found before in pre-industrial rocks? The most prominent place is the basement of the Reese impact crater, which is about 15 million years old. That's in Germany. And also there are 3.5 GA impact spherules from the Barberton group in South Africa, and they're interpreted as being from a giant impact by a comet. And the chrome isotopes of the Barberton spherules indicate a cometary origin, as do the chrome isotopes on sediments from the Cretaceous Tertiary boundary. So here are pictures of impact spherules from Precambrian rocks. This is the Jurina. These are from Bruce Simonson. So they're mostly from the Hammersley area. The Jurina and the Dales Gorge are both from the Hammersley group. At the Widenum, I'm not. I think it's also. So here's the spherules in thin section, and here's the spherules in a larger section, and these are the impact spherules. And what's interesting is, the impact spherules that they found were from a really big impact into the ocean, and the only ones that you can find in the Precambrian are the ones that are from really large events, because the other ones just get recrystallized in such a way that you can't be sure what they are. So these are really, really big events. And some of these have chrome isotopes indicating a cometary impactor. So where are all those metallic high melting point grains coming from? I don't think they should be present in the original cometary material because it's all low melting point. So I came up with this cosmic wet dust mop idea, that the metallic grains are swept up by comets as they move around the solar system and outside the solar system. And so basically the high melting point grains of iron, nickel, and chrome, they accrete to the outside of the comets, and then they're subsequently lost as the comet degasses passing the sun. And the metal flakes are then incorporated into meteor streams, but they can also contain carbon derived from the comet. So, I mean, and what we observe with comets is that when they're near the sun, they look white because they're degassing. But once they get away from the sun, the surface of the comet becomes black again. So basically it's covered up by dust. So I mean, there are observations that support the idea that comets kind of sweep up dust as they move around the solar system. And so here's the dust mop idea, testable hypothesis. So basically, the thing is, the comets with orbits that go further out in the solar system are more likely to accrete the primordial tin-rich grains, either from interstellar place or perhaps the Oort cloud. I mean, I'm not sure if any of these go out far enough. I can tell you that Halley doesn't go out into the Oort cloud. And comets with orbits passing near through the asteroid belt are more likely to accrete the Fe and I-rich grains, because those are probably originally asteroidal in origin. And so what I'm guessing is that comets with shorter orbital periods are less likely to be sources of the tin-rich grains, because it's not every meteor shower that contains tin-rich grains. And it's interesting because here's a list of periods. Halley, 76 years. And then you have Swift-Tuttle has a long period, 133. And then Temple-Tuttle, 33. And then the others are all really short periods. So when we get all it sorted out, if this is right, then it seems likely that the tin-rich grains will come from Halley, Swift-Tuttle, and maybe Temple-Tuttle. And the others won't be a significant source. And remember I said, okay, I got to go back to something because. So notice, okay, they think that Tunguska was in late June, and they think that Tunguska was from the Taurids, but notice that the Perseids also, the Perseids are kind of more spread out. And I think they're harder to observe. So it's possible that the Tunguska body came from the Perseids. So, and so that's, oh, I got to go back to the meteor showers because I have a list of which meteor shower goes with which comet. So when I did the comet speeds, I should have asked. Okay, so the Perseids, they're from Swift-Tuttle, and Swift-Tuttle has a long orbital period. So it's possible. So Temple-Tuttle and Swift-Tuttle and Halley are the ones that have the long orbital periods. And so they're the ones I think that would be most likely to be sources of these tin-rich grains. But we got to try to sort out the geochronology of these grains a little better. And also look for, in the two cores from the Hudson River, figure out, so it's Temple-Tuttle. Yeah, Swift-Tuttle's great. It's got a period of 133 years. So, and it's the source of the Perseids. So, so yeah, I think it's probably these three. And the big question is, can we, when we look at the data, does it turn out that all of the tin-rich horizons were either at times that would be fit with a pass of Halley, Swift-Tuttle, or Temple-Tuttle? Because another thing that is sort of implicit in all this is once that comet passes the sun, the tin-rich grains are probably going to be lost because they'll melt, they'll come off. So basically, the tin-rich grains have to be picked up each time you go through the solar system. I don't think they can just stay with the comet. And so where does the tin come from? It's generated through the long S process. And it's generated in quite a few stars, masses of 60% to 10 times that of the sun. And what I haven't been able to find is what percentage of stars would form tin. So, I mean, tin isn't that common, so probably not so many. But if we're seeing, if some of this, if this tin is actually interstellar dust, then it would be coming from an asymptotic giant branch star. And I have no idea how far away the nearest asymptotic giant branch star is. So, conclusions: tin-rich cosmic dust is very rare. It's like 1 in 1,000, but there are horizons where it's much more abundant. And some past manifestations are definitely associated with comet Halley. Others cannot be sourced from Halley. And possible source comets are many, but association with Enki is unlikely if the West dust mop idea are correct. So comets with the longest periods that are in Earth-crossing orbit: Halley, the Eta Aquarid, and Halley has 2 meteor showers: Temple-Tuttle, the Leonids, and Swift-Tuttle, the Perseids. And the question I have is, could all the incursions of tin-rich cosmic dust come from passes of these comets? So the Tunguska impact was during the time of the Perseid as well as the Taurid meteor showers. And historical records show that the Perseids have been active for more than 100 years, and that the orbit of Swift-Tuttle has not changed much over time. So that's it. Do you have any questions?
Thank you very much, Dallas.
You're welcome.
Please unmute yourself if you have questions. I know there's still a lot of people out there.
Yep.
Yeah, there's quite a few people out there. I just got to see the gallery.
Rich, you have a question?
No, it was quite complete. Thank you.
Yeah, I'm very excited about this because, you know, we found those tin-coated forms a long time ago, and we didn't really know where they were coming from at all. We just knew that they couldn't be, they were not industrial tin because the stuff was way too old.
Just say, we ask about this space dust. I've remember hearing about how much the Earth takes on every day from dust and debris in the solar system.
Yeah, I mean, there's a lot of it, but I
Yeah.
mean, the stuff that comes in slowly, you can't really see. I mean, well, one thing, there's a daytime, there's meteor showers where it always comes in the daytime, and they don't know very much about those because they can't see them. And then they're, if they're coming in slowly, then they don't show up because they don't produce light when they hit the atmosphere. So it's hard to track what stuff is coming in.
So we can all go into our backyard and find some?
Yeah, if you did it right, you'd get a whole lot more industrial pollution though.
Some of this dust collected by airplanes that they have filters, they fly through the atmosphere, and then they.
Yeah, that's right.
Is that how it's done?
I think they may go up in balloons and do it. I think balloons are maybe a little more friendly for that.
Yeah.
So I think they send up unmanned balloons and get it. That's one way. I don't know if they do airplanes or not. Does anybody know just for sure whether or not they use airplanes?
outside my knowledge.
I think I mean, this stuff, I think you need something that's moving more slowly because you've got to get you've got to get a wind across wherever you're collecting. I know for a while they were collecting cosmic dust. When I was out at sea, they had a thing in the bow of the ship and they were collecting dust just from the bow.
Hmm.
Because you're far from land and they were just using it. I don't know how much cosmic dust they got or if they were just trying to look at. I mean, you could get a lot of things. If you're at sea, you could get stuff from red tides, you could get, just oceanic aerosols.
Salt,
But
salt, yes.
yeah, salt. So they were collecting stuff at the bow of the ship.
Okay, I think we've just about reached the limit of my time.
Thank you.
Thank you all very
Thank you.
much.
Thank you. It
Next
was nice
month,
to
we're
see
going to
you.
be going into deep time with Alberto Malavano.
So who's the next person?
Alberto,
About Malinverno. So what's he
Yes.
going to talk about?
he's going to talk about deep time.
Oh, that's pretty cool.
That'll be on the 17th.
Oh, okay.
And then the following month, I have a young graduate student at the Columbia Water Center who'll be talking about water supplies around the world.
Huh. Cool.
And that'll be on the 17th of December. Alberto is on the 19th of November.
Okay.
Dallas, I'll send out a all Lamont message about Alberto.
Okay. Yeah. Deep time is a really interesting concept. Yeah. Well, nice to see the people I can see. Renee and Richard and Ruben. And,
Thanks very much. It's a lovely day out. Everybody go kayaking.
yeah. I'm going out for sure. Although
Where
I
you gonna go?
Many more of those.
pardon?
Where you
Not too
going?
many more of those coming.
Yeah. No, it's beautiful out.
Dallas, where are you going to go?
Oh, I'm not going kayaking. I think we haven't been that much in the summer. I'm just going to go walking. Actually, I have kind of problems with one of my knees right now that I'm trying to fix. So kayaking is not really recommended.
Okay.
Too hard to
Been
get
there.
in and out of the boat. But I'm looking forward to, I had a really bad injury 2 years ago and it's my arms are better now. Just now got to get the knee back. The whole body, it's creaky, but I'm doing well. We just bought a house in Maine because we're going to retire there. So we were up there and I loved it. It was so nice. And it's right off a lake. So there's all kinds of lakes. So
Enjoy it.
yeah, I think we'll really enjoy it. We're
I
right,
have a-
right a couple hundred yards from the town swimming area, town beach, which is a
Good.
really nice beach. So
Good. I have a boat that's screaming at me to take it out.
okay, we'll
right.
enjoy for sure.
Okay. Hope to see everybody next month.
Yes,
I
thank you.
got
Okay,
it.
thanks.
See ya.
Take care.
Thanks, Dallas.
Bye-bye.
Bye.
Thanks, Dallas.
Goodbye.
Bye-bye.